So the most simplest one that you can find in the literature is a priori algorithm. Okay, there are two steps: finding all the frequent item sets. That means the ones that have support greater than the threshold of minimum support. Okay, they are called as frequent item sets, obviously. And using these frequent item sets, you generate rules. And as we said, we'll focus only on the first part because 99.9% of the time is spent in this phase alone. Okay? So, like for example, from here, chicken, clothes, and milk is a frequent item set. And using this item set, you can generate a rule of this sort from this item set. Okay, that's the first phase and the second phase. Now, let's talk about the first part, which is finding all the item sets. And we already said computing, enumerating all possible subsets is very expensive, right? Like whatever we draw on whatever we wrote in the text pad, which is same as this, right? At the lowest level, you have one item sets, and then you have two item sets combining multiple of these, and then by combining multiple of these, you can compute three item sets, and so on. You can go on, right? So all of this is called a lattice of item sets. Okay. So essentially, you are taking all the subsets and then putting them in a nicely structured manner. So, for example, A and B together form AB, A and D together form AD, and so on. And then similarly, AB, AD, and BD form ABD. Right? So, in other words, the ABD subset consists of two subsets, which are AB, AD, and BD. And each of these contain one subsets. Okay? So all the lines essentially are the subsets related to this thing ABD. Okay? So this is a lattice of item sets. And what is the naive approach that we talked about? We simply go to every possible item set in the lattice and then enumerate its frequency. Okay? And obviously we said it's very inefficient. And now we want to find an efficient way to traverse through the lattice. Okay? Like the Tanai's intuition, which is a dynamic programming, comes from this fact. Right? If you know the frequency of A and B, you can use it to compute the frequency of AB. Similarly, if you know the frequency of AB, AD, and BD, you can compute the support for ABD, and so on. Right? So one simple mechanism is to go in a level-wise manner, bottom up. First, I find all the item sets from the first level. Then I go to the second level and compute them, and then third level, then fourth level, and so on. That's a reasonable strategy, right? And the Apriori algorithm essentially follows that level-wise search in the lattice. Okay? Is it clear so far? Okay. Now, what I'm going to tell you is the most fundamental property of frequent item set mining. Every single algorithm that is presented for this problem use this particular property. Okay? And what is that property? It's very simple. It's basically based on the notion of frequency. Okay? So, let's say AB is frequent. Okay? That means AB support is greater than the threshold. It occurs in more than threshold number of transactions. Okay, if I tell you that AB is frequent, can you say anything about A and B, which are the subsets of AB? Can I say they are frequent or not frequent, or can be both? Can you say anything about it? If AB is frequent, can I say A is frequent and B is frequent? Absolutely, right? Because if the frequency or if the support of AB is greater than the threshold, then obviously support of its subsets will be greater than threshold. Okay? It's a very, very simple property. Do you agree, Tanay? Okay. Now, let's look at the contrapositive of that statement, which is if A is not frequent, okay? Let's say A occurs in only 20% of the transactions, whereas our threshold is 30%. Okay? Can I say anything about AB? If A is not frequent, then obviously AB is also not frequent, because frequency of AB is less than or equal to frequency of A. Right? And that gives you a very great power. Right? Since you are going in a level-wise manner, as soon as you find something is not frequent, so what is the meaning of A is not frequent? Then you know that AB is not frequent, AC is not frequent, AD is not frequent, ABC is not frequent, ABD is not frequent, ACD is not frequent. So you can prune out all this part of the search space. You don't need to enumerate and evaluate these item sets. Right? So you are able to skip a lot of these item sets for evaluation because you know that they will not be frequent. Okay? This is called as pruning the search space. I have exponential search space, which is this entire lattice. As we said, it's an exponential size, 2 to the n. And we are pruning out some parts of the search space based on that property. If an item set is not frequent, then none of its supersets can become frequent. Okay? So just by knowing A is not frequent, I can cut out a lot of these guys. I can cut that. I can cut that. I can cut that. I can cut this. I can cut this. I can cut that. Okay? Now suddenly you just have 4 more things to evaluate instead of 7 and 10. Right? From 10 you quickly went to 7. Now if you know that, let's say, D is also not frequent, okay, then you can cut down even further. This is not frequent, this is not frequent, this is not frequent. So you just have BC to evaluate. Okay? So you see how quickly we are able to remove some of the things from the search space. Okay? So that is called as a priori property, or also called as downward closure property. Okay? Downward closure because essentially if AB is frequent, then all its downward things are also frequent. So it kind of encloses those things. So that's why it's called downward closure. But the property is essentially any subsets of a frequent item set are also frequent. In other words, the contrapositive of that statement is if an item set is not frequent, then none of its supersets can be frequent. Okay, that's a contrapositive, which is the most important property. Okay, do you understand that? Okay, now if you know that, then that's it. A priori is done actually. So what you need to do, essentially that iterative algorithm. So you find all the frequent item sets. That's very easy, right? I tell you that my Walmart dataset contains 10,000 items. I simply count in one scan. I can count all the frequencies of all the 10,000 items, right? I can simply create a hash map of 10,000 items or array of 10,000 items, and then I'll keep scanning every transaction, and then I increment the corresponding counts, and at the end of my scan, I will have the frequencies or the support of all the 10,000 items that I have. Okay, and then I can quickly, once I compute that, I can find which of them are frequent and which of them are not frequent, right? Because I simply count which ones have frequency greater than the threshold, in our example 30%, and which of them have less than 30%. Okay, so let's say I have 6 items. Okay, let's for the purpose of an example, so I have A, B, C, D, E, F. These are 6 items. Okay, now what is the first step I am saying? Find the support of all 6 items. Okay, and the second thing, that is, this requires one scan of the data, entire data. Okay, and then I can simply find the list of frequent items. Okay, in other words, frequent one item sets. Are you with me so far? Okay, now let's say in this example I have A, C, E and F are frequent. Okay, and then B, D and what's the other one? Oh, that's it, are not frequent. Okay, now given this, which of the 2 item sets, so I am done with the first level that contains 1 item sets. Now I want to go to the second level. Okay, but we can use our downward closure property and remove some of the things from the second level, right? So if I know that these 4 are frequent and these 2 are not frequent, can you list the list of item sets, 2 item sets that we need to evaluate, right? Like for example, should I evaluate AB? No, because B is not frequent. Can I evaluate CD? No. Can I evaluate EF? Yes. Okay. So, you know, I mean, you understood the concept. Now, can you list out all the item sets that need to be evaluated? 2 item sets. Okay, Subrata, your answer? Absolutely. So both of you are absolutely correct. I need to evaluate these guys. I simply copy pasted Tanai's answer, which is same as Subrata's answer as well. That means I need to only look at my frequent subsets and then create the candidates for the next level. Okay, so these are my candidates. Now, what can I do? Once I compute the candidates, the next step is find the frequency of all candidates. And how would I do it? I can do another scan of the data. One more scan. And then compute the frequency of all these 2 items. Okay? And then I can again divide that into frequent or not frequent. So let's say for the purpose of example, AC, AE and CE are frequent. But however, AF, what are the remaining? CF and EF are not frequent. Okay? That I can do after my second scan. Now, the next step is obviously I have to compute 3 candidates, 3 item set candidates. Okay? So what would be the candidate subset I need to evaluate here? Actually, let's even make it interesting. Let's make this also frequent. Okay, there are 4 frequent and 2 not frequent. Okay, now how can I or which of the 3 item sets that I need to evaluate in my next level? Can I evaluate CEF? The answer is no, because EF, for example, is not frequent, and therefore CEF cannot be frequent. Okay, so CEF I won't evaluate. And let's take ACF. Do I need to evaluate it? ACF, is it, what are the subsets involved in there? AC, AF, CF. No, AC is frequent, but AF is not frequent. So even if one of them is not frequent, then I can quickly remove the entire guy. So since AF is not frequent, I will not, I cannot have ACF to be frequent, right? That is the power. I mean, you can quickly prune out a lot of things. So similarly, AEF, do I need to evaluate that? AEF, no, absolutely. How about ACE? This would be yes, because it is frequent. I mean, it is a candidate, because what are all the subsets in there? AC, AE, CE. And if you see, all those 3 are frequent. Since all of them are frequent, it is a candidate. Okay, so that means I just have a single candidate that need to be evaluated. So essentially, what you can do is simply by looking at these, just like here, right? How did you come up with this list? You looked at these, and then you took all combinations, AC, AE, AF, CE, CF, EF, right? So similarly, take this and then compute all combinations, okay? So AC, AE, what's the combination? ACE, but also I have additional constraint that for ACE, I should also have CE. So CE is there, so ACE is a candidate. Now let's try to combine AC and CE, which will come up to the same thing. Now let's compute AC and CF. That means ACF. But it's not possible because AF is not there. So similarly, you compute this and this, which is ACE, which you already have, AE and CF. That's not a three combination because it's a large one. AE, CF, that's a 4 combination. So we'll look at the 4th level. And then compute CE and CF, CEF. And again, that's not possible because EF is not there. Okay? So you see the method, right? You can simply look at the frequent items, take all the combinations, and then compute the next level candidates. Okay? That's it. You keep repeating until you're at the final level, or you don't have anything more to try out. Like for example, this is my candidate. Now what is my next step? Find the frequency or the support of ACE. Let's say ACE is not frequent. Do I need to evaluate any 4 candidates, 4 item set candidates? No, because there's nothing to expand on, right? So that would be my end of the algorithm. So after this, my output is simply from the first level we got ACEF, from the second level we got these another 4. So the total output of the algorithm is 8 subsets that are frequent. Okay? So you can see, right, how many computations you did. In the first level, you computed frequency of all the 6. In the second level, you computed the frequency of another 6 items here, 6 plus 6, 12. And in the third level, you computed only one item set, which is actually 13. So out of 24 or 23, not even 23. So what's the combination total? 2 to the 6 minus 1 is equal to how much? 63. So out of all the 63 combinations, you simply evaluated only 13. Okay? You can see the power of that simple rule. Okay? That's it. That's your a priori algorithm. You simply find all the frequent 1 item sets, then list all the 2 item sets and so on. Okay, so in the next slide I have a detailed example if you want to see, which is similar to what we just talked about but with respect to a particular data set. So you can scan item sets, so you get candidates of 1 item sets, that's what it is called as C1. And then what here the minimum support is 2 out of 4 transactions. So this guy is 1, so you cut it out. And then these are my frequent items, and this is not frequent item. And then you combine these frequent items to compute C2, candidates from the second level. Okay, and then you again scan the database, cut something out, and then you find all the other guys that are frequent, and then you combine these to make the third item C3, candidate of 3, and then you keep progressing. Okay, Any questions on the algorithm? As I said, I mean, the algorithm is very simple, right? Once you understood the concepts of support and confidence, algorithm is fairly straightforward, at least this one. Okay? So, in our example, the one that we have here, how many scans on the data that I have? How many scans of the data that we did overall? How many scans? Is it 1, 2, 3, 4? How many scans do we have? So, we said for computing the frequency of individual item sets, we need to scan the data to compute the frequency, right? So, my question is, how many of those scans that we did in this particular example? There are 3 scans of the data. No, not 7, 3. Because in the first level, we did 1 scan and then found all the frequencies of all the 1 items. Then we computed the candidates from level 2. Then we did 1 more scan to find frequent and not frequent of level 2. Then we computed 3 item set candidates. And in order to compute that frequency, we will need our third scan. We compute the frequency of ACE and then decided it's not frequent and we will stop. So that means we did 1, 2 and 3 scans. Right? Make sense, Subrata? So, in other words, we are making a scan for every level in the data set. Right? So if you think about it in the lattice context, here we make 1 scan here, 1 scan here, 1 scan here, 1 scan here, and so on until wherever you stop. Right? So the downside of this algorithm, even though it's very simple and very powerful, the downside of the algorithm is that we are making repeated scans of the data at every level. Okay? And you can imagine, right, if you have 10,000 items, you will go up to many levels, maybe 30 levels, 40 levels. If I have terabyte or 10 terabytes of data, I have to scan this data 40 times. That's a lot of time, right? Okay, so that's the negative point of this data. Many scans over the data set. And further research is on how can we cut down on the number of scans while computing these item sets. Okay, there are many algorithms, and the most popular one is called as FP growth, which is extremely efficient. I mean, it has some limitations, but it is in general it's extremely efficient, and it makes only 2 scans over the data, guaranteed. Just by scanning the data twice, you compute all the item sets. Okay, and therefore it is very efficient. Okay, but I mean, we won't go into the details of that algorithm, which is a little more complex. But this is the algorithm that got implemented in Mahout. Okay. Any questions? Does that? So that concludes our algorithm description of the entire thing. Any questions? Okay, so yes, that's what my next step is, showing it in Mahout. Okay, so obviously in order to do that, we need to have a data set. Let's look at this particular data set. Okay, so here I have the first column as a basket ID, something like transaction ID. Okay, and I have a bunch of items: air conditioner, lemons, standard coffee, frozen chicken wings, 98% fat-free hamburger, sugar cookies, onions, ham, blah, 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 blah. Many of them, right? There are a lot of them. Okay, these are all the different items. And there is a false. That means this transaction did not have this item. And if you look at, for example, this is a true, right? That means the transaction number C8582 has items sugar cookies and onions, and also ice cream, and maybe some other ones. You can see it in the right side of the screen. Okay? So wherever there is the item that was bought in that particular transaction, there is a true, and remaining all the things are false. Okay? So this is like a 0-1 matrix. If the item was bought in that particular transaction, you have a 1. Otherwise, it's a 0. Okay? So this is the different representation of the data. Do you understand this? Subrata, is that clear? So it simply says C8582 contains sugar cookies, onions, and ice cream. Okay, so that's why we have true associated with those items, and remaining all items are false. Okay, so essentially if I look at our example data, this one, right? I have how many items here? 1, 2, 3, 4, 5, and 6 clothes. Okay, so there are a total of 6 items: beef, chicken, milk, cheese, boots. Beef, chicken, milk, cheese, boots, and clothes. Okay, there are a total of 6 items. That means I'm representing this as a 7-by-6 matrix. 7 is a transaction, 6 is the items. Okay, clear, right? Let me draw that example. Okay, beef, chicken, milk, cheese, boots, and clothes. Okay, now T1 will be beef, chicken, and milk. So essentially true. So let's put 1 and 0. 1, 0, sorry. 1, 1, 0, 0, 0. And T2 will be what? Beef and cheese. So 1 here, 0, 0, 0. This is 1, 0. Okay, you get the idea. Right? So this is another representation of the data. And in this case, there are some implementations which take this representation, and there are some implementations which take this representation, which is just simply the list of items. Okay? And Mahout implementation requires this representation. Okay, list of items as opposed to this Boolean representation. Okay, but since our data is in this format, we have to convert from here to here and then feed it into Mahout. Okay.